capacitance. And separated by a dielectric medium in between this. This is any two conducting surfaces separated by an insulating medium exhibit the property of a capacitor. The conducting surfaces are called electrodes and the insulating medium is called dielectric. A capacitor stores energy in the form of an electric field that is established by the opposite charges on the two electrodes. The electric field is represented by the line of forces between the positive and the negative charges and is concentrated within the dielectric. The amount of charge per unit voltage that is capacitor can store in its capacitance and denoted by the letter as C, and the units are farad. 1 farad is the amount of capacitance when 1 coulomb of charge is stored with 1 voltage across the plates. Capacitance C is given by Q by charge per voltage, or you can write C equals to Q by small v. We know that I equals to dq by dt. You can write this C equals to dq by dt divided by dv by dt. Then this will be I by dv by dt. Then I equals to C dv by dt is the relation between current and voltage in a capacitance C. And the symbol of the capacitor is the voltage dV is given by 1 by C and dV. Integrating on both sides, we'll get, now integrate, then 0 to t, then v of t minus v of 0 equals to 1 by c integral I dt. Then v of t equals to 1 by c integral I dt plus v naught initial value. Then a power P is given by V I, that is V I, we have already seen that C dV by dt is power in watts. Now energy W is given by integral 0 to t P dt and integral 0 to t Vc dV by dt dt. And you can write this C as a constant, you can keep it outside, 0 to t v dv half cv square. The energy stored in a capacitor is given by half cv square. From all these equations, you can conclude, first one, the current in the capacitor is 0, that I equals to 0. If the voltage across it is constant, that V is constant, or there is no change in voltage, that is nothing but the magnitude, which is nothing but a DC value. For DC values, dV by dt equals to 0, so current is 0. A small change in the voltage, that again point to that if V is changed to V plus at t equals to t naught, even this is a small change, but t value remains 0, then this total value will be infinite. That means the current is infinite, which is not possible practically. So we can say that in a fixed capacitance, the voltage cannot change abruptly or suddenly, which means capacitor don't allow the sudden change in the voltage when there is a finite current. Third point, the capacitor can store a finite amount of energy W even though current I equals to 0. Since the energy going to depend upon capacitance and the voltage, So I at that time may be 0, but if you see this formula, you can understand even current I is 0. The terminal voltage is initial voltage that will be there, and that voltage is going to produce some energy. So W will be there even I equals to 0. Then fourth one, a pure capacitor never dissipates energy but only stores. That is why it is called non-dissipative passive element. But practical capacitors dissipate power due to internal resistance. The practical capacitor dissipates power, so they can call as lumped elements.